Hey guys, it's Mr. Post, and on today's video we'll be checking out work and energy and checking out the relationship between the two in different scenarios. Let's read the problem here. The 2,000 kilogram car is at rest. That's kind of an important thing for us. We're just going to acknowledge that right now. It's at rest. At the top of a 10-meter hill. Once again, it's pretty important for us to the height of the hill. How fast will it be going at the bottom? And we're going to assume no friction. Now, the formula we'll be using is this. The total mechanical energy initially plus work is going to equal the total mechanical energy in the end of the scenario. Now you got to remember, energy has to be accounted for. We can't really just lose energy, and if we do lose energy in a system, we do want to know where it went. Now the total mechanical energy comes in the form of potential energy and also kinetic energy, and they're going to be added together to equal my total mechanical energy. Work, as you know, is either going to be a positive or a negative thing. Now positive work adds energy to a system, and negative work takes energy away from a system. And on the reverse side here, the final conditions, we want to know how much potential and kinetic energy we have at the end, or really how much total mechanical energy. I do want you to see, though, for the sake of math and formulas here, in doing our calculations, we are going to refer to PE using the formula mass times gravity times the height of the object. We'll be referring to the kinetic energy by using the formula 1/2 mv squared, and we'll be calculating work using our work formula, which is actually going to be a force times a distance. Now today I think I'm probably just going to use and give you a joules, quantity of joules for work, so that might not be needed force times distance. And likewise on the reverse side, we're just simply going to refer to and calculate potential energy with mgh and kinetic energy 1/2 mv squared. Alright guys, let's start off here. Okay, so the facts are that we have a car that is at 10 meters of height over the lowest point. And so from that, I can determine that I have a mass times gravity times height. And so my car has a mass of 2,000 kilograms. It's going to be multiplied by my 9.8 meters per second squared, my acceleration due to gravity, and the height of the object is going to be 10 meters. Now, for the initial conditions, I also want to add in the kinetic energy and work. But now we know it's at rest. So if it's at rest, my velocity is 0. All right, so that's at 0. If that's at 0, 1/2 mass times 0 squared, we're not going to have any kinetic energy because the object is not in motion. Now, the question also says, at the top of the 10-meter hill, how fast will it be going at the bottom? So we're kind of going to go over here and say, we're looking for my velocity. Problem doesn't tell us that work was done. So really what we're looking at here is that the object has potential energy in a certain amount of joules, and it's going to equal a certain amount of joules on the other side. And work is not lost. So energy initially is going to equal the energy at the end. So let's crunch the numbers here. 2,000 times 9.8 times 10. So initially we have 196,000 joules of energy. And that's how much we had in the system, and because there is no friction in the system as the problem shows, energy is not lost. And so really I need 196,000 on the other side. And that 196,000 is all velocity. And so it's all kinetic energy. When we're going to calculate 1/2 mass of 2,000 kilograms times velocity squared. Now from this, we're going to use some algebra and solve for velocity. And when I rearrange the equation, I have 2 times 196,000 joules divided by 2,000, which is the mass. And I'm taking the square root of that because this is v squared over here. So in order to find the velocity, I need to take the square root of that. And we end up finding that the velocity of the object at the end is equal to 14 meters per second. But once again, one of the driving points of this whole entire problem is that work is not being used. And if work's not being used, then my total mechanical energy initially needs to equal the total mechanical energy at the end. It's only when work is done on the object will I see a difference in my energy in the final than it was in the beginning. Okay guys, in this example, a 2,000 kilogram car again is at rest on the top of a 10-meter high hill. And I want to know how fast will it be going at the bottom, but this time I have friction exerting 110,000 joules of work. So we're looking at the same exact formula. The initial conditions plus work now is going to equal the final conditions. And the one thing you're going to see here is that for the work this time, I'll have 110,000 joules. In this case, it's friction which means negative work. So we're looking at, we're going to have less energy on the other side in the final part of the problem. The problem sets up as the same as last time, and we had mass times gravity times height. So let's use that again. We have mass, which was 2,000 kilograms, times 9.8, and times a height of 10 meters. This time, though, we're looking at adding a negative 110,000 joules of work. Now, friction is work that removes energy from a system. And you prove it by saying if there is friction, the car is going to slow down over time. If you're slowing down over time, you have less kinetic energy. So we're definitely losing energy from our system. So let's crunch the numbers, guys, and let's find out how many joules of energy we have in the left side or the initial part of the problem. And so what we're looking at here is 86,000 joules, and that's exactly 110,000 joules less than we had last time. Now that is going to be converted 100% purely into kinetic energy of the car. Now once again, I'm not using potential energy on this side because I'm assuming the lowest level is going to have a height of 0. So we kind of base this as 10 meters high, and over here this would be considered 0 meters of elevation. So I really don't have PE on the final conditions. I have strictly kinetic energy. So we're looking at this is going to be equal to 1/2. The mass was 2,000 kilograms, and times my velocity squared. Okay, guys, rearrange the problem and solve for your velocity. And what we end up here, guys, after we rearrange the problem, we have 86,000 times 2 divided by 2,000 kilograms, and we need to take the square root of that in order to find our velocity, and we solve for the velocity of 9.27 meters per second. And you're going to remember from the last problem, this car was actually going somewhere around 14 meters per second at the bottom of the hill. Now it's only going 9.27. What happened to that? We lost some kinetic energy. Kinetic energy was lost because friction stole the energy as the car went down the hill. Now when I say friction exerts 110,000 joules of work, that is friction along this whole entire surface. This is a force acting over a distance. If we knew the distance, we could probably calculate the force of friction as well. In this problem, guys, a 3,000 kilogram car approaches a really tall hill going 20 meters per second. And we're going to say how far up the hill will it go, and we're also going to make two assumptions here. We're making an assumption that the driver is letting off the gas pedal and you're coasting up the hill. And we're also going to make an assumption that there is no friction. So if there is no friction, that means there is no work, and there is no positive work either because we're coasting up a hill. Now, I want to find how far up the hill I'm going to go. And how far up the hill I'm going to go really depends upon when do I stop. And when I stop, I'm going to have no velocity. If I have no velocity at the end, I have no kinetic energy. Now, if we're going to the problem and we set the lowest elevation right here to be 0 meters, and this elevation to be a certain height, well, if we're coming at 0 meters, we actually have no potential energy either. So what we're going to look at here is that the object is traveling with a certain amount of kinetic energy because it's going 20 meters per second, and all of that kinetic energy is going to be converted into potential energy, and we should be able to solve for how high we're going up the hill. Alright guys, let's set the problem up. When we plug in the numbers, we find out that 1/2 times 3,000 times 20 squared will result in 600,000 joules of kinetic energy. On the other side, that has to be converted into pure potential energy because there is no loss due to energy due to friction. So we have over here is 3,000 times 9.8, and I've kind of simplified that down to 29,400 multiplied by the height. At this point, you need to isolate for the height, and we find out that the height is going to be equal to 20.4 meters. So over here, it looks like we're going up 20.4 meters, and that is simply converting all of my kinetic energy that I have going into this, and it's going to be stopped at the very top of the hill. At the highest point it will reach is going to be 20.4 meters, and that is now it has pure potential energy where it once had kinetic energy.